Hello, this is Lab 4 by Zach Braun. In this presentation, we're going to have an introduction, a tracker video analysis, fundamental principle discussion, and analysis of the computational model in VPython. We're going to talk about what it all means, and we're going to have a final conclusion at the end. The problem for this lab is to model the complicated motion that would be seen in extreme rope sports. It really appears complicated at first, but it is easy to use and understand using the two fundamental principles, Newton's second law and the energy principle. The results that we get from this is that both of the fundamental principles correctly help and predict the motion in the extreme rope sports example. Let's now look at the tracker video. This is my tracker video. The initial setup includes that the mass is 0.402 kilograms and the initial distance that I'm showing right here is 0.7 meters. I also set my coordinate axis at the very top of the fixed point. It is set with the negative y going down, positive y going up, positive x to the right, and minus x to the left. Let's now watch it in motion. You can see in this graph of the x versus t that it oscillates back and forth. Here is the y one. The y one oscillates back and forth as well. The starting position was negative 0. The starting time in the x was negative 0.105 and the starting point in the y was negative 0.627. Let's now look at the fundamental principle that allows this action to occur. Let's now talk about the fundamental principles. To start off, we have the period of oscillation t equals 2 pi square root m over k. This then, after manipulation, takes us to k equals 4 pi squared m over t squared. I then plug my numbers into it and I get k equals 5.853. I then measure the oscillation to be 3t equals 4.94 and divide by 3, t equals 1.64. The mass is in static equilibrium, so force of gravity equals force of the spring. mg equals k sub s and mg equals k L minus L naught. And force of the spring equals negative ks L, s equals L minus L naught. I then use my numbers and I get 0.0269 meters. Second fundamental principle that we use is delta E equals delta K plus delta US plus delta UG. No energy leaving the system, 0 equals delta K plus UG plus delta US. And for those individual ones, K equals 1 half mv squared, UG equals mgy, US equals 1 half ks squared. This then can lead us into our Python code. This is my Python code copied and pasted into a PowerPoint. The first thing I changed is that I added in my mass, which was 0.402 kilograms. And then I changed the initial vector to negative 0.105, negative 0.627 like I showed in the tracker video. Next we have the time step, which was delta t 1 over 210. I thought this time step was small enough. And then g equals 9.8 because we're near the center. G equals 9.8 because we're at normal atmosphere. And then my k sub s, I showed how to calculate that in the fundamental principle. And I just plugged it in here. I also showed how to plug in the L naught, which is right here. And then L equals ball.pos minus spring.pos. And L hat equals L over mag L. And S equals mag L minus L naught. Those three are just taken straight from the formulas themselves, which I showed on the fundamental principle part. The next part of my code deals with the energy. The energy fundamental principle is delta E equals the sum of all the energy changes, and that is delta K, delta UG, and delta US. And K equals 1 half mv squared, which put in this is K equals 1 half ball.m mag ball.v squared. Then potential energy is ball.m times g times ball.pos.y, and the spring potential energy is 1 half times k underscore s times s squared. This is the end of my code. Now let me show you how it runs. Let's now watch my module run. The blue is the force of the spring, and it changes and is dynamically changing from smaller to bigger than the force of gravity. The force of gravity is a black arrow, and it is always static and pointing straight down. The red ball is my CSV data that I predicted using Tracker. The red ball is my data from the CSV file. The red line on my energy graph is the spring force, and it has the same oscillation as the period that my tracker did. The green arrow is opposite the spring force, and it is the potential energy, and it is also in the same oscillation. It's always opposite in phase compared to the spring force. So the spring force goes up, force of gravity goes down, and vice versa. Delta K is the blue line, and it oscillates twice as fast as the spring force. Then the yellow is the total energy change in the system, and as you can see, there's no energy going out of our system, so it is 0 the whole time. This is also evidenced by the red and the green always canceling each other out, making the yellow. Let's now look at what does it mean. What does it mean? The first question is the energy principle satisfied? The energy principle is satisfied because no energy leaves the system, evidenced by the two facts. The total energy, which was in yellow, equals 0. And the second fact is that the spring force and the gravitational potential energy force are in the same oscillations but different signs. Therefore, they cancel each other out. The second what does it mean question compares the oscillation periods in both the x and y and we need to see what happens. T sub x equals 1.647 seconds. T sub y equals 1.2 seconds. T sub x has only one force acting on it, and that is the spring force. T sub y has both the spring force and the force of gravity counteracting each other, and therefore that is why it has a smaller value. This concludes Lab 4. Thank you for watching.